In a previous video, we were listening to the audible signals produced by a Geiger counter. The Geiger counter is a detector sensitive to ionizing radiation. The duration came from a mineral containing natural uranium and all the products in the decay chain. This means that the mineral emits a mixture of alpha and beta particles in the range of different gamma rays. Nevertheless, the detector gives the same signal, an audible click sound, and does not distinguish between what kind of radiation it was that caused the signal, and it was also independent of the energy of that radiation. All that is necessary is an ionization caused by the incoming radiation inside the sensitive volume of the detector. The Geiger counter is a gas-filled detector. Normally it's a gas, a noble gas, for example helium, neon or argon. Detectors are typically tube-shaped and they have a thin entrance window separating the gas volume from the surrounding. Because it's a sensitive thin window, it's normally covered with some extra protection, and if I remove that, maybe you can see the thin quartz window that separates the surrounding from the gas volume on the inside. Ionizing radiation has the ability to ionize atoms, hence the name. Examples for these ionizing radiations are alpha particles, which is a helium-4 nucleus, beta particles, which can be electrons from so-called beta-minus decays, or positrons from beta-plus decays, and gamma rays. Further, and maybe less common examples, are also neutrons or fission products. The energy carried by the particle, kinetic energy in most cases, is eventually transformed to other types of energy until the particle is finally stopped and absorbed. In the case of alpha particles, helium-4 nuclei, resulting for example from alpha decay, the kinetic energy leads to a series of ionizations in the medium along the track, for example the air around the source or the gas inside our Geiger counter. And gradually the alpha particle is slowed down, the kinetic energy has been used to ionize a number of atoms, and the particle eventually steals them, when it comes to rest, 2 electrons and becomes a neutral helium atom. Now, different types of radiation interact in different ways with the matter they pass through. Gamma radiation, which is electrically neutral, ionizes via the so-called photo effect or via Compton scattering. If the gamma rays have very high energies, they can also undergo something called pair production and transform into an electron-positron pair. Without going into further details about interaction of ionizing radiation with matter, let's just conclude that the energy released from the nuclear decay in the form of ionizing radiation leads to a number of ionizations in the surrounding material. The question is then how to detect these ionizations and hence detect the presence of ionization radiation coming, for example, from nuclear decay, some nearby source, or from cosmic radiation. One method to detect these ionizations is using a Geiger counter. Alpha particles create many ionizations in close proximity along their tracks. One talks about high energy loss per unit distance or a high linear energy transfer, LET. And hence a number of free electrons are created along that track, and they can produce a very clear signal in the detector. Gamma rays, on the other hand, they ionize much more sparsely, and they might only have one interaction inside the sensitive volume of the detector, or maybe none at all. So the trick of the detector is then to be able to detect even single ionizations in order to be sensitive for the detection of gamma rays. Now, to achieve this, the Geiger counter uses an electric field that accelerates the electrons towards a very thin anode wire. The anode wire is in the center of that cylinder, and we need to apply high voltage from the outside. The electrons are accelerated in the electric field and can create additional free electrons. These electrons are then also accelerated towards the anode, freeing even more electrons. And in the end, a considerable avalanche is produced that leads to an electric signal that is large enough to be distinguished from electronic noise. The avalanche leads to a short collapse of the electric field, ending the production of further free electrons. For a short time, the detector is insensitive to new ionizations, and the gas ions have time to recombine with free electrons, restoring the detector's possibility to detect radiation. So it is due to this avalanche amplification process that the detector does not distinguish between radiation types or the energy of the radiation. It just registers, counts incoming particles. Other types of detectors have capabilities to identify particle types and measure their energy. They act as spectrometers. As a final remark, I would like to point out that not all incoming radiation is registered. One reason is due to the short periods of insensitivity after detection of a particle. This is called the dead time, and it's dependent on the count rate. The main reason, however, is the probability of the incoming radiation to interact with the gas in the detector. Alpha particles are so densely ionizing, they have such a high LET or energy loss per unit length, that the detection probability is practically 100%, provided, that is, that the particle hits the sensitive volume. That means it reaches the detector and manages to pass through this thin entrance window that I showed you earlier. This can be a challenge for alpha particles for the very reason that they ionize so densely. They are easily stopped, and as you may know, typically an alpha particle from decay travels something like 4 centimeters in air and can be absorbed by a sheet of paper. Now, gamma rays are an entirely different story. The reason is that their interactions with electrons in the atomic shells are of a very different nature. And that is because an alpha particle, an electron, they carry charge, while a photon or a gamma ray does not carry any charge. So the interaction of the gamma ray with matter is called the photo effect and Compton scattering. And again, at very high energies, also pair production. The probability of an incoming gamma ray that passes through the detector without any interaction at all is actually significant. Factors like the type of gas, the gas pressure, and of course the size of the detector matter. For this reason, one normally calibrates detectors against sources with known strength. Then again, the Geiger counter is fairly simple and cheap and hence an excellent means to measure increased presence of ionizing radiation. However, due to the earlier mentioned limitations, they have limited capabilities to be used for measurements of radiation dose, etc. They are perfect for demonstrating the different stopping power for various kinds of radiation. And so, as a final example, I will use different types of radiation, and we will see how easy or how difficult it is to stop that radiation.